Right, so I'll be talking about big data optimization, which is a field I'm working in. Of course, since this is OR Society event, I should have to start with the OR Society logo, and not to create too much suspense. Of course, this is what all of us think about the science of better, right? So now it's out. So this is what we think. Of course, since I'm talking about optimization, what I want is the science of best. Optimization is the science of best. You want the optimal solution, and there's just one optimal, or there could be more optimal, they're equally good, and they're all best. So that's the science of the best for me right now in this talk. Right, so the outline of this talk, I'll speak about, for a while, about data science, big data, and optimization in general. Some general musings about these terms and what they mean and so on. Then I'll outline some applications of data science, intersection, optimization, intersection, big data. There are so many, so I'll really just outline a few of those to highlight certain properties of the structure of optimization problems related to big data. And then the second half of my talk, I'll spend on introducing several tools which have been developed in the past several years. The starting tools are pretty old, but as I progress, these tools get newer and newer, and they are the key enablers of big data optimization technology. And feel free to interrupt me at any point in time. In fact, I don't particularly enjoy listening to my own voice. So I'd be really pleased if you can speak up, ask anything during the talk. The second half of the talk is structured in such a way that I don't have to go through all of these tools. I can jump through. So if we have a discussion, it's completely all right. Good. So the first part, by data, what I mean is just anything that has potential value and that you have in digital form. And if you don't have it in digital form, just take a snapshot of it with a camera and then it's data, right? So data is anything that has potential value. Could be text, video, images, scans, whatever you wish or will. And data in data science usually modeled statistically or as a signal in signal processing. By data science, we've seen several definitions of what data science means. I don't want to get into philosophical debates about data science. So let's just adopt this working definition. Data science is extraction of knowledge from data through any means possible. Statistics, OR, could be any tool, mathematical tool, computer science, and so on. And by machine learning, as a distinction from what data science means, there's this word automated. So the process needs to be automated. So it doesn't necessarily have to involve humans. It's automated learning from the data in order to make predictions, but also possibly decisions about unseen data. So what I mean by this, I'll make it a little clearer later on as I go. Right, so we've seen a diagram of this type earlier in the debate, some including one. It's not my own. It's one of those many diagrams out there. And I'm not trying to say that we should adopt this definition, because obviously if you're a data scientist, you come up with a diagram where data science is in the middle. If you're an OR person or analytics person, that's in the middle, right? So it's always your field in the middle. That's not the point. The point is that this is one way of looking at what data science means. And of course, it is a much more complex concept than something that can be explained by intersection of three things. There's more things involved, and when you take this intersection, maybe the intersection of everything will be empty in the end. But the point is, there has to be some mathematical modeling, mathematical tools on the table if you're talking about data science. At the same time, there has to be some computer science stuff. It has to work. It has to be programmable. You have to have a tool which can be run, right? An algorithm or software or something like this. And at the same time, you have to have some expertise in some subject area. So airlines, supply chains, it could be biology, any domain expertise has to be there as well. So this is what I mean by data science. And just to underscore that when you get into these diagrams, you can very easily get astray. So you can come up with diagrams of this type, right? This is evil, right? And so on. So it's very easy to have fun about these diagrams. And when you Google these diagrams, you can find all kinds of alternatives. Awesome. So in data science, what we do is that we collect all the tools out there in order to achieve our goal. So for instance, if we need some matrices around, we use matrix theory. If probability, probabilistic reasoning, probabilistic algorithms, or any kind of probability is needed anywhere, so robustness, these kinds of concepts, stochastic programming, then we use tools from probability. If machine learning is something that will help us to solve the problem, we use machine learning. If the problem is large enough and we need to use big computers, we use high-performance computing. So essentially anything, linear algebra, complex analysis, function analysis, even operations, it doesn't matter. All the tools which can help us to solve the problem, they're being used in data science. So I'm part of the Alan Turing Institute. Alan Turing Institute is a joint venture of these 6 partners. So it's ABSERG and 5 universities. The Alan Turing Institute is the national UK Institute for Data Science, and it was founded just a year ago, so it's very, very young. It's being developed as we speak. And what it wants to do, there are these 4 pillars: foundational research, so which is something we're all familiar with. Then translational research as well, so the research of the kind which will be useful for some industry. Then training the next generation of researchers. At the moment, Alan Turing Institute, we're starting a PhD program in data science. The first cohort will start in October. There'll be 15 to 20 students every year for the next several years coming in, all based in London at the British Library. And also there's some postdocs, fellows, and so on. And then also the Alan Turing Institute wants to be at the center of a public discussion about data science in the UK. There are some strategic priorities of the Alan Turing Institute. I welcome you to visit the website, download the document, and this is actually copy-paste from the document. As you can see, the Alan Turing Institute has come up with these 6 priority sectors for translational research. And I'm sure that OR can actually has something to say about all of these, all 6, right? And at the same time, there are these 4 key capabilities which Alan Turing Institute has identified in the founding partners. And these are mathematical representations, which is at the heart of OR, and understanding human behavior as well, decision making and so on, which is at the heart of OR. There are some other things, system and platforms, which is more computer science-y topic, but it's very important as well if you want these things to have impact and to be working somewhere. And as a product, then you have to have a system, you have to have a platform which actually runs this. And inference and learning, these are areas closely related to statistics and machine learning. Right, so what is big data? Well, there might be too much hype about big data. So we've seen this life cycle of every concept early today. And the New York Times said that big data opens the door to a new approach to understanding the world and making decisions. So which is a bold statement. But of course, there's also another citation from early today, which will very soon become a classic. So you can pick any of these. So what I mean by big data is data that can't be stored or processed on a typical system. So if you have something running on a mobile phone, on a cell phone, and you can't process it using the traditional ways on the phone, it might be big data relative to the mobile phone. If you have something that normally the problem is being solved on a desktop computer and you can't any longer use a desktop computer because maybe the data size is too big, then you have to use more computers, that's called a cluster, and so on. If a cluster is too slow, you have to go to a supercomputer. If a supercomputer is too slow, you have to wait a couple generations, right? Then you just can't do anything, right? So this is what I mean by this. And once we have these huge quantities of data, it's not just the amount of data, it's not just the storage itself. You have to do something fundamentally different if you want to solve problems which are described by big data. The reason for this is that the traditional approaches would simply not work. They'd be too slow. And I'll highlight this a little bit later on. So for instance, you can have an approach which works iteratively, as all algorithms do, but in every iteration, in every step, it's buzzing a little bit, right? I'm just about to shoot off, okay, no? Am I good? All right. So which iteratively reads all the data that describes the problem in each iteration. Now, if you have a big data problem, you cannot do that. Okay. Is it this one? No? Okay, put it here. Is it better? It's better. Okay. Okay, good. So, and you can easily see now that if you have a problem which is described by, let's say, 10 terabytes of data, and you have such problems out there, you can no longer rely on an algorithm which in every step, and there might be thousands of these steps, reads the entire 10 terabyte data set. That is not possible. But if you use an algorithm of the type of, let's say, gradient descent, okay, I'm not assuming that you're familiar with this, but it's a basic tool in big data analysis and big data optimization. I'll describe it later on. Then that's exactly what you would be required to do. You'll be asked to read entire data set every single time step. And that is just completely infeasible. You don't have that much time at your disposal to do this iteratively for thousands of iterations. So you really have to come, you have to really redesign the routes, the algorithmic routes of how you approach the problem. So in the same way as linear programming was transforming industry back then when OR was born, right now there are new approaches to solving big data optimization problems, also optimization problems by coincidence, but of a different type, not linear programs, but convex optimization problems. And new approaches are being born which enable us to solve these huge problems much more efficiently than ever before. And that's what's a key enabler of big data technology right now. So once you work in big data, of course, these are the kinds of taxi tickets that you get. And this is a taxi ticket I actually got years ago. And I was giving, after I was returning from London when I gave a big data talk, and I was wondering, does the taxi driver know that I'm doing big data? I think I was just supposed to pay $9.96, but somehow this is what he gave me. Of course, I didn't pay. And I didn't use my extra grant to cover this. All right. So optimization of big data means a couple of things to me. One thing that it means to me, and this is a shameless plug for a conference that I established and run in Edinburgh since 2012, is the name of a conference series we run in Edinburgh around May every about a couple of years. And this is a logo which I helped to design. So I'm really proud of that. Right? So big data problem is the big thing. You're just pushing up the hill. It's optimization, you're maximizing. Good. Right. At the same time, optimization really plays a key role in big data analysis in several completely different ways. Well, one way is the following, that if you look at what machine learning is, you look at the machine learning theory textbook, then you realize, and people realized this only quite recently, just several years ago, that in fact, one way of formalizing machine learning is that it is equivalent to stochastic optimization, which is part of OR. Just equivalence is the same problem. If you write down formally the main problem in machine learning, one of the key problems in machine learning, it is equivalent to stochastic optimization. It's minimization of an expectation of some functions. That's it. So there's this kind of an answer. That optimization plays a key role in machine learning, obviously, because it's equivalent to stochastic to machine learning. Another way of looking at this is that optimization is the tool to train machine learning models. So whenever you have a machine learning model, it will have some parameters. When you would want to fix these parameters, you will run an optimization algorithm which will decide on these parameters. For instance, neural network, there's lots of parameters. You fit them by running an optimization algorithm. It will not be a linear program, so it's not our favorite and most useful and most widely used algorithm. It's not simplex method, but it's a different optimization algorithm which is being run there. And mostly it's some variant of stochastic gradient descent. I don't know how many of you have heard of this, but it's optimization, so it's OR. Then optimization is also used in discovering new data representations. So for instance, when you have a picture, you can represent the picture in a digital way in many ways. One way is the sequence of zeros and ones. That might be useful for some tasks, but completely useless for other tasks. For instance, if you represent an image as a sequence of zeros and ones, right, or numbers, intensities, pixel intensities, you can quite easily denoise the image. If it's noisy, you can denoise it. Or if it's blurry, you can deblur it, which is a data science task that maybe nobody here is interested in, but still is an example. But with that representation, you'll have trouble identifying faces in the image. You need completely different representation to identify faces in the image. And for this, neural networks are used to come up with a good representation of the image. And in order to find the right neural network, you have to use optimization there, in that phase. So there's completely different use of optimization in big data analysis. And at the same time, optimization is used then in turning all of this into action. Right, so in big data problems, optimization objectives are not just any kinds of objectives. Usually, what's happening is that the objective, the function that you want to minimize, is formed from data that you collect. Okay, so it might be a least squares problem where the matrix are some measurements, okay, some downloads, and they can be images. And since there are some measurements, they're very imprecise. Maybe you don't have enough of them. If you have more of them, the objective changes, right? Because of this, you don't need to solve these optimization problems to really high accuracy. Because already the optimization problem, which is modeling your problem, is inaccurate. So why would you go beyond that inaccuracy, that error? Okay? Which is a huge step change in the paradigm for solving optimization problems. Because with algorithms such as Newton's method, interpolation methods, these are amazing algorithms which can solve medium-sized problems to high, to pretty large, but not really big data problems. They can solve them to any accuracy you want. But these are the kinds of things that you don't need in big data analysis. And since you don't need them, you need different algorithms, which can maybe do much better. And the objectives are often simple. So there's not that much going on in the modeling part. These are very, very simple objectives. And the idea is that, okay, let's do the algorithm, do the modeling. Right? I'm not going to come up with a very complicated, let's say, mixed integer program. I'm coming up with a very simple, let's say, data fitting problem. And since there's lots of data, the data itself will discover the structure in there. Okay, so that is part of what's going on there. So for instance here, you may have a so-called LASSO problem, which is least square regression plus this, well, okay, this is not LASSO, okay. So this is ridge regression. If this was one norm, it would be a LASSO problem. And all the data is in here, in this matrix A, so this could be terabytes, could be gigabytes, could be very, very large matrix. And by solving this, you do some sort of a fitting, but the solution itself will tell you what the model would be in the end. Right, so now I'll stop. The first part is over, and if you have any questions about any of what I just said.
If you're Sisyphus as your icon.
Okay. So that was a question?
Yeah.
Okay, could you repeat that?
Why did you choose Sisyphus as your icon to your compass?
Okay, so why did I not use Sisyphus as the icon? Okay, I'm repeating because they wouldn't hear you, so that's why I'll be repeating. I don't know. I could have easily chosen that.
Quite a bad paradigm.
Yeah. Yeah, good suggestion. Next time you invite me, I'll do that. Okay, good. Any more questions? Please feel free to, let's have a discussion. Yep.
Earlier I was saying to Stuart that I could get your view of the words data science as a decision-neutral technology which becomes more and more overwhelming, I'll be honest, to the business of how we physically handle the terabytes and whatever it is of data that have got to be handled by someone. And it is a technology thing with it's hardware, it's software, I find I start from computers actually, in third generation stuff. You're saying, oh no, it's got a role in decision making as well, except that so far you've not steered your decision making in any particular area of thinking.
Right, so the question was the data science, whether it does include decision making in the end or not. I'm not going to repeat the entire question. I think this was the essence. And in some sense the answer is yes, but not enough. So for instance, when you go to YouTube, right, you will see a recommendation of videos. Now, there were some decisions being made by someone to recommend these videos to you. Right? Decision making has taken place, except no human did that. It's automated decision making. So data science is about automated decision making, and it didn't yet move that much towards what we would like. It's something more in connection with actual humans making decisions as a support system for humans to make decisions. So there's some of it, but it's not decision making, let's say in the OR sense. Okay. Okay, I'll take one more and then I'll keep going.
Could you make a comment about
Sure.
the quality of data?
Okay. Right, so if I could make a comment about the quality of data. Well, it's a big issue. Of course, you can have data where you have missing data. You can have data where it's heterogeneous of different types and you need to integrate it. There's huge systems issues, huge data cleaning issues, and data quality issues as well involved there. I don't do research in that area, which means I cannot make any reasonable comment, anything informed, but I'm aware that these issues are there and research is really needed into that area as well. What I work on is once you have the clean data, how do you process it? And I'll address those issues. All right, so now, okay, maybe one more and then I'll go.
Is non-linearity necessarily embedded in all the data science problems, or could there be some linear problems as well?
Non-linearity is not necessary. No, that's not necessary.
So there could be applications where you have the underlying.
Yes, definitely, definitely. So the main idea is that the problem itself has to be defined through data. So when you have, let's say, a mixed integer program, it shouldn't be a model that somebody thought of, but the parameters there, many parameters there should be actually collected data. Once you have that, any objective is fine, and it's a data science problem. So now I have to continue. Thank you very much for these questions. So now let me briefly enumerate some of the applications in data science, and this is really, really very incomplete. So there's natural language processing of all kinds, speech recognition, and so on and so forth. Text processing, again, you can have machine translation or spam filtering. These are all automated decisions have to be made about something based on data. And you cannot make a decision that these kinds of emails will be spam without looking at the email itself. It is data-informed decision making. Image video processing, social networks, online advertising, even scientific measurements. And this is a very incomplete list. So let me go into some of these. This is just a picture that I just flick there and then I just go away, okay? It's one of those things. Right, so image deblurring. So here is a very particular problem. You take an image and it's blurred and you'd like to get this image, which actually we got with one algorithm that we developed with my co-authors. This is a data science problem. You might not be interested in it, but in fact, the algorithm used to do this is something that can solve completely different problems that you might actually be interested in. And it's scalable and so on and so forth. So what is really going on here? How can you go from here to here? In fact, I'll spare you of all the details. This is the problem that needs to be solved. And you can see it's extremely simple. So what's going on in here? You have just least squares objective, where this right-hand side B is the blurred image. How can a vector be image? Well, you just put the pixels, let's say row-wise or column-wise, stack them all together, and you get one huge vector containing all the pixel intensities of the image, right? So it's a huge dimensional quadratic in the image size of vector. Then X is the image that you would like to reconstruct. That's the deblurred image, right? Now, N is the number of pixels in the image, right? So the bigger image you have, and there you immediately see it's big data because you take a photo, that's data, right? When you have many of those photos, it's even bigger data. When you have more megapixels, it's even bigger data. So this N will just keep growing. Then there's A. Some expertise has to go into this. How is this A formed? And in fact, there's some blurring matrix involved. It's multiplied by a wavelet basis matrix. One doesn't have to go into the details here. It's a certain very specified matrix. The idea being that in this sort of new representation, in this new basis after the wavelet transformation, natural images tend to be sparse. Okay? Natural images are just not any kinds of images. When you know that the natural image will be sparse and you add this L1 penalty here, which is just this function generalized to multiple dimensions, just bunch of absolute values on these individual coordinates. It turns out, as you keep increasing this lambda, the output will be more and more sparse. There will be more and more zeros in this wavelet basis. And it turns out that's just the right thing to do. You do that, you solve the problem, and you get the deblurred image. Right? So you can see it's very simple. You just throw all the data in there. In this case, the data turns out to be in this B, not in A. Okay? And you solve this. And as you keep fiddling with this lambda, you get different outputs as images. Right? And you need to have an algorithm now which is scalable. You cannot run something which you cannot run. Right? I mean, you cannot run, let's say, gradient descent because it will take forever. And I'll explain what that is. Right. So here is a completely different problem. And I would even say this is not that much data science, but there's a reason why I want to include this. So we have worked on Truss topology design, which is some sort of engineering. What you want to do is you want to build a bridge. You want to build a truss which will be as stable as possible. And again, if you're not interested in bridges, don't worry about it at all. Even I'm not interested in bridges, in fact, okay? So the thing is, you have this green line here, and on this green line, there'll be downward force pulling down because that's where the bridge is supposed to actually be. That's where the cars will be passing through. And then you want to find where these blue lines would be. You want to figure that out and how thick they should be and where they shouldn't be. And that's going to be the support of this bridge. Now you go into the physics of this, which I don't understand, but I read up on it, right? And I go through the end, and in the end you realize when you write down the physics, you get this problem to solve. Okay? It's exactly the same problem. Exactly the same problem. Now in this matrix A, now you have the physics encoded, and the sparsity, x is actually visible in the picture because x has as much dimension as there's the number of potential bars in the discretization. So in fact, the solution will be sparse. You can see that most of the potential bars are not there. They are zeros. That's precisely what the L1 thing will do. Okay? It will make sure you don't use that much steel in your truss, in your bridge. Right. Here's another fun problem. It's also imaging problem. So you want to go from here over there automatically without any input whatsoever. How do you do that? Well, it turns out if you solve this optimization problem, it does it. Now there's lots of magic going in between, which was done by Alina and co-author in their beautiful paper. And they first formulated a submodular optimization problem, which is a discrete kind of optimization problem over subsets. Then they reformulated, and they reformulated again, and then this is what they get. And if you look at it, it's a quadratic minimization problem of a very specific kind. So that's all you should remember about it. It's just quadratic, nothing else. Even simple quadratic, because there's no kind of Hessian in there. But there's some constraints. So all of these vectors xi have to live in some sets, and they happen to be polytopes. So if you replace this objective by linear objectives, this is just some sort of a linear programming problem, right? Because you'll be maximizing linear function over intersection of some polytopes, right? Or actually not intersection, but kind of union, right? You know what I mean? So, so it's a small departure from linear programming, but suddenly by doing this, you can do image segmentation. Right, so here's another one. So I guess most of you have heard in the news about the progress of AlphaGo and that it bet and that it won against Lee Sedol in Go. And behind this is a complicated system behind, but one of the things that's going on behind is training of a neural network. And neural network is nothing else, just a very strangely defined function. There are some inputs, here are some outputs, there's some linear transformation in between, and some nonlinear transformations on the nodes. It's just a way of writing down a function in a complicated way. When you train the network, you have to solve this optimization problem. So I'm skipping through the steps, but when you're training a network, this is exactly what you have to do. You have to minimize the average of a huge number of functions. Why do you need to minimize the average of a huge number of functions? Because each function corresponds to one data point that you collect. So when you train over images, each function corresponds to an image that you collect. If you train over videos, each function is defined by the entire video. So it could be several gigabytes of data just describing Fi. And you want to minimize the average over all of these images, let's say, all over these videos, over all pieces of text, and so on. When you do that, you have trained a neural network. And these functions will be non-convex, which makes it very difficult to train the neural networks. And the question is, how can we do this? Well, without recent advances in optimization, this would not be possible. We would not be able to train these huge networks, and then we would not have these beautiful kinds of news in the news. Right, there's phase detection, recommender systems. In fact, one of the algorithms I'll describe today is implemented here in YouTube. Geotagging, exactly the same algorithm solves this geotagging problem, which means you just collect tweets, and from the tweets you want to infer who is where. Where are these people coming from? So these people, this is not my work, so I'm not trying to figure out who is where. but they have used an algorithm that we designed to do that. So this is in fact the map of Europe created from geolocated tweeters. So this is where they are, so they're kind of everywhere. Right, spam filtering, ranking, all of this you can do. Right, so now I will describe one application in a little bit more detail, and then I move into the third part about the methods. So this application is the one which maybe you might be most interested in, is this training of these networks, of training of classifiers. So this is what's going on. So imagine you have data in the real world, and it can be any kind of data. So let's say pieces of text, news from New York Times, right? And you represent the data as a matrix in some way. And I'm not telling you right now how, but usually this is done, let's say, using bag of words approach, where you just create a matrix in such a way that you count all the words in the article. You don't care about the order, just count them and have a big matrix telling you, okay, this word is there this many times, and so on and so forth. That's one naive approach. Like, there are many different approaches. So somehow you represent whatever the data is as a matrix. So it could be video, image, anything. And then you attach some label to this data point. So for instance, you read this article and you realize this is an article on politics. Or this is an image, and you realize, well, there's a cat in the image, so I'll categorize as a cat image. That's what the label means. And you keep collecting these data label pairs. And you would want to learn from these connections as a little baby is learning when they're learning language, they're learning object representations in the world. You would want the system to automatically learn just from these data label pairs to infer a label from a data they have not seen before. So then you show the system a new image, and you want the system to say, oh, there is a horse on the image, automatically, without anything. So how is that done? And it's actually very, very simple. So here, I'll completely describe what's going on. It's very simple. So what's going on is the following. You assume that the data is out there in the real world with some distribution. So you kind of model it statistically. But you don't assume you know what the distribution is, right? So for instance, when you collect images from the internet, you will not collect all of them. If you collected all of them, you would know exactly the distribution, right? You can just compute the empirical distribution. But you can't do it. So you only subsample, and based on that, you will be able to somehow maybe guess what the distribution would be. But in no place in this procedure, you will need to actually write it down what the distribution is. So it's there, and this is what you want. You would like to figure out a vector W. Okay? So somehow imagine, I give you vector W, so I figured it out, and then I tell you how I figured it out, such that you give me a new image which I have never seen before. Okay? So let's say these AIs are images. I do this product matrix times vector, okay? Just simple matrix times vector product, and out of the product I get some number, yi, okay? And that will tell me what the label is of that image. So that yi will tell me this is a cat, or this is a horse, or this is a movie on this topic. That's what I want. So it looks like magic. How can I get that? And this is how I do it. I first define a loss function, which is a loss between this product and the label. It could be some sort of a distance, but it doesn't have to be distance. It could be something asymmetric, doesn't have to be positively homogeneous, so it doesn't have to be actually norm. Some sort of a proximity measure. I decide on this, and depending on what this loss is, could be logistic regression, could be squared loss, and so on, you get different types of models. And then what I want to compute the expected loss over all the images that are out there on the internet that I don't even have. Okay? And imagine that I give you such W which minimizes this expected loss. Imagine. What would that mean? It would mean that I have this W, which now I think of as an algorithm. The W, the vector itself, is an algorithm, which will have the smallest expected loss in terms of recognizing the category of the image, even though I don't know the expectation. Right? So that is the goal. Now, how do I do that? Well, I cannot minimize this expectation. Minimizing this expectation would be stochastic optimization problem. Right? I cannot do it because I don't know the distribution of the expectation. I cannot do that. So what I do is something that you can actually guess. So is there anybody who's willing to guess what I'll do instead? Instead of minimizing the expectation, who can come up with that? Any guesses? I don't know distribution, so I can minimize the expectation. All right, there's no guesses. This is what I do. I just collect a lot of data label pairs. Okay, just a lot of them. And that's why I have big data immediately, because I want to approximate the expectation by the sample average. Okay, so it's just law of large numbers somehow. Right? So this sample average is an approximation. This creates kind of an approximation, unbiased approximation of the expectation. And I need a lot of data label pairs because then I will have a good approximation. So the more I have, the better approximation I have. So suddenly what I want to do, I want to minimize average of a huge number of functions, which is just the problem I told you was the problem behind the training of the neural network in the AlphaGo example. Right? So that's the problem, and you can abstract from the particular structure of the loss, and this is the kind of problem. And you solve that somehow, and when you solve it, then you have solved your problem and you have the predictor. All right, so now pause again, and then I'll move into the last part about these tricks, how one can possibly minimize these functions efficiently. There is a question.
So how do you spot the black swans?
The black swans. I've never seen one. Is it okay? So yeah, actually there's a. So I should repeat. How do you spot the black swans? I've never seen one. There's actually a very interesting story that a colleague of mine, a machine learner, Shai Schwartz, told me. So he's coding up these algorithms for self-driving cars, and he showed us a video in one conference when he's driving the self-driving car. It didn't crash, but he told me that and told us in that workshop that somehow the system has trouble figuring out what the tunnel entrances are, because sometimes the tunnel entrance looks just like a car, and if it looks like a car and the system thinks it's a car, you just want to go around and then just hit the side of the tunnel. And but then he figured out a way how to avoid this, and did something like a black swan. So somehow the system doesn't know these things exist, and then you have to modify a little bit, and it can be learned with some extra few examples. So one answer would be, if you just add few more examples of these black swans, if they exist, if you know them, then the system will autocorrect. Otherwise, no. Any more questions? Yeah.
So presumably all of these approaches, they're the sort of thing that quite rapidly scale to very large problems.
You mean the methods themselves?
I mean the applications.
The applications, yes, they quite, yeah, exactly. So in fact, as we collect more and more data, we're in this big data era, so we cannot escape it. The data will be here. The only question is what we do with it. One thing that we can do with it, we can just throw it away. Yeah? Or most of it, and work with a smaller data set. That's one approach. Another approach is to actually deal with it in a different way. And I'll talk about some of these ways later on, just outline them. And ideally, you would want to have a system which scales linearly somehow with the data size, or even better than that. Right? And traditional algorithms don't have that property. They scale terribly with data size. So when you have a Newton's algorithm has to solve the linear system in each step. So it depends quadratically on the data size in each step. That's completely forbidden. You want to be done before one step of the Newton method. That's what you want to do. And the only way you can actually do it is because you don't need that accuracy that Newton method is giving you. You only need small accuracy, and the reason why you only need small accuracy is because the problem itself is formed from some collected data, so you don't need 10 digits of accuracy, or 15 or 20. Right? Okay, so now I have 16 more minutes or so. Right? Okay, to talk about some of these approaches. And so for me, optimization with big data is really like extreme mountain climbing. So I always get relief when I realize that I don't get enough exercise. At least I know that my algorithms get enough exercise for me. So the algorithms are climbing hills. Okay, it's happening inside the computer, right? And I'm not getting leaner because of it, but at least I can sleep better a little bit. Right, and big data usually means that all of this hill climbing is happening in a hugely dimensional space. Right? So you're not minimizing a one-dimensional function or two, but a billion-dimensional function. How can you do that? Right, well, when you have this algorithm, you're there in one step, right? Right on the top. But we usually don't have that, so we have to walk. So you have to have an iterative algorithm that just keeps going, and somehow you hope that you get to the top if you're maximizing, or to the bottom when you're minimizing. Right, and now these are some of the tools which have been developed in the past decades to years in big data optimization, which have proved extremely, extremely useful to tackle big data problems. So some of them date back several hundred years, such as gradient descent back to Cauchy. But handling non-smoothness, that's already pretty new, just a decade or so. Acceleration, well, it was discovered at some point and then forgotten for 20 years and then rediscovered again. And then randomization, that's already pretty new. It's just several years. In some form, it existed for longer, but in the new form, it's very fresh. And then parallelization, mini-batching, together with randomization, these are additional tricks. All of them are orthogonal, and they can be used together to create a new, much faster algorithm. So these are not tricks which you have to pick from. You can combine them, but I will present them one by one. And I will probably only do, if I go really fast, just the first four. These things I already knew I would have to give up on. And I had this as a backup in case I couldn't get any discussion out of you. But I could, which is great. All right, so here is a brief, biased, and severely incomplete history of big data optimization. So Cauchy discovered gradient descent. Then Nesterov discovered accelerated gradient descent. And I jumped over several centuries. Well, one, okay. Then there's the age of interpolation methods, which many of you know that this is something which much of optimization community was really, really into in these 2 decades after linear programming was developed very well. And then somehow this age stopped. There's still some research going on in this area, but everybody in the optimization field started doing gradient type methods. And that was around the year 2000 or 2004 or so, when again Nesterov discovered that some non-smooth problems are as easy as smooth problems. So there's no more divide, fundamental divide between non-smoothness and smoothness. This seems like a theoretical concept, but in fact, many real practical problems are non-smooth. And if you can solve them only slowly, then you're doomed. But if you can solve them really quickly, then everything is fine. And that's what Nesterov figured out. Then there is randomization, and now you start seeing why this is severely biased and incomplete and so on, because I was involved in that as well. And parallelism, duality, and some other things, all of these things can be combined, and now is the age of the new tricks, and I will have no time to talk about those. So, gradient descent. How many of you know about gradient descent? It's a good number, but not everybody, which is good, because I have a couple slides about this, so now you'll know. So this is the idea of just follow ball rolling down the hill. When you want to minimize a function, just walk up the hill, bring some big heavy ball with you, and just release it. And where it goes, that's gradient descent algorithm. Just goes down the hill. That's it. So algorithmically, you just want to follow that line, and that line is the line of steepest descent. So you compute the gradient, the negative gradient will point in the right direction. So when you want to minimize a function, just any function, let's say it's convex and smooth, doesn't matter if you don't know what these things are. I don't want to be precise about what exactly I mean by convexity. In fact, I mean strong convexity, and by smoothness, I don't mean I have all kinds of derivatives. It doesn't matter. Just one derivative is fine. This is the gradient descent algorithm. So you take your previous xk step, subtract some multiple of the gradient, and then what's going on is if you were here, you go down the hill, you're here, you're going down the hill, if you're there, you're going down the hill. Just keep doing this iteratively, and you get to the bottom eventually. That's it. So it turns out that if the number of iterations, number of steps of this procedure, of this hill climbing, or actually is climbing an inverted hill, is at least a certain number times logarithm of 1 over epsilon. So this number is some sort of a number which describes the shape of the hill, some sort of a condition number, okay? If the hill is bad, the number is big, okay? then you are within epsilon of the minimum. That's it. This is a theorem. This is true. Okay? So all you need to know is this number about a hill. And when you know this number, this logarithm is nothing. It's just a small number. You can ignore it. So if your hill has certain condition number, that's the number of steps you need to take in order to climb the hill. That's it. Or descend the hill. Right? Since we're minimizing. So this is a theorem. Now, this is all beautiful and nice. But the problem with this in data science is, and this was the first kind of algorithm that was tried in data science, like a decade ago or so, is that this gradient, when you compute it, you need to look at all the data describing the problem. You need to read all the data. That amount of work is required to compute the gradient. So if you have a 10 terabyte data set of images, in order to just compute the gradient, you need to read the 10 terabyte data set. And that takes a long time. And gradient descent is not a particularly fast algorithm. So what will happen is you will need to take tens of thousands of steps of this algorithm, and you will be never able to solve the problem unless it's not so big a problem. Right, so then there's this idea of acceleration, where Nesterov figured out in '83, and then it was completely forgotten because the age of interpret methods started. And then in 2003 it was kind of rediscovered again by Nesterov when he realized he can do some other things with it. The gradient descent can be made much, much faster. Well, here I just failed to show how much faster it can be, but this is supposed to mean that it can be much, much faster. You can see that the error just, there's several degrees of magnitude difference. And the cost of doing this is just 2 gradient evaluations. You just modify the algorithm a little bit. I will not tell you how. I want to abstract from actually going into the detail. You just compute 2 gradients, that's all, instead of 1 per iteration, and you can do much, much better. So, and mathematically it means that you can replace the condition number by square root of the condition number. Right? So if the condition number is million, then you get square root of million, which is much, much less number, much less steps, right? So the thing is better. And everything I'm going to tell you about, and there's not much because I only have 8 minutes after this acceleration trick can be thrown on top of that, right? So if I use randomization, or if I have a distributed algorithm, or if I use duality or anything, I can always throw this acceleration trick on top of that. And it took the community that actually involved some work, right? It was not completely trivial to see that, but the community managed to do that. So you always can accelerate in this way. Right, so acceleration was, I think, one of the main reasons why this era of interpret methods translated into the era of the gradient type methods, and which enabled much better, much quicker data science solutions. It is also known in the literature as a momentum trick. So if you look at the deep neural network literature, they use algorithm called stochastic gradient descent with momentum. Momentum means acceleration, it's the same thing. Right, and this can be combined with all kinds of other tricks. So here is another trick. If you have a problem which is non-smooth, such as the L1 minimization one is, the LASSO, right? The one with the Truss topology design with the bridge, and the one with, which one was that? With the reconstruction, with the image reconstruction, with the Deblurring. They had this L1 thing, this L1 norm, right? Absolute values. That's a non-smooth thing, right? It's pointed down there. Non-smooth functions are much more difficult than smooth functions. Well, Nesterov said no. Some non-smoothness is as simple as if the function was actually smooth. And the basic idea is the following. When you have a function which is a sum of a smooth function, which is nice, everybody loves it. It's a beautiful, smooth, nice, quadratic, let's say, whatever. And this is ugly non-smooth thing. Sometimes minimizing the sum of these things is easy. And as easy as if this was not there at all. Right? Think of this as just these least squares, and think of this as the L1 norm. And this is how it's done. Well, first you pretend, you close your eyes, and you pretend that the non-smoothness was not there at all. Okay? So you see, I'm just taking a gradient descent step, and I'm pretending G doesn't exist. Okay? Of course, I cannot pretend forever because then I would not solve the problem. So then I take a second step, which is called a proximal step. That's why this is called a proximal trick, where I do this very strange thing. Okay? What actually this is doing, I'm minimizing function G perturbed by a very simple quadratic. Okay? imagine that this problem is actually very, very easily solvable. This is not always easily solvable. But for many functions, such as the L1 norm, if G was L1 norm, then this thing has a closed form solution that I can write down. I don't have to run any algorithm. Good. There's 3 cases, and I know exactly what it is. So it's completely easy. In those cases, this is very easy to do. It doesn't take any time at all. And then, by doing this repeatedly, you actually solve the non-smooth problem. And it will take exactly the same amount of time as if the problem was smooth. Okay? So the condition number or square root of condition number if you have acceleration. Exactly the same thing. So it's a beautiful trick, and it's used now everywhere in data science. Literally everywhere. Arg min means that you take the minimizer. Min would be the minimum, and arg would be the argument of the minimum. So it's the x, the solution. Right? So you solve this, and xk plus 1 will be the solution itself, not the function value. Okay. Right. So that is what is done. And if you think this is mysterious, in fact, in a special case, there is a very simple explanation. So when I have 1 more minute, could you just let me know if I have 1 more minute? Okay. So there's a very simple explanation when this G happens to be 0 or infinity on some convex set. If it's 0 on some convex set and infinity outside of convex set, then in fact what's going on, you first take gradient step and then you project onto that convex set. That's exactly what's going on. This is the proximal step. Gradient, project. So projected gradient algorithm is a special case of this for this particular G. Okay? Right. Now, at least I want to do this one thing and then I stop. It'll be pretty quick. Maybe I can even manage into 4 minutes 2 of these things. We'll see. So tool number 4. And this is, I think, very counterintuitive for many of the decision scientists in the audience. That somehow we figured out that doing many simple decisions is better than doing a few very smart ones. Okay? Which sounds really, really weird. It sounds stupid in some sense, right? Why would I want to do many stupid decisions and then claim it's better than very few very smart ones? Well, I'll just keep this thing. So I skip this thing as well, and I'll talk about this thing. Right? So there's this idea of randomized coordinate descent. And the idea is the following. You want to minimize a function, let's say this function, you want to get here. Right? And in order to minimize it, you could compute gradient, it will point you right there. But instead, I'm going to flip a coin, which means I'm making a random decision. I flip a coin, and the coin tells me go east or west. And I decide to go east because that is down the hill. So going west would be up the hill. And I'm going down the hill eastwards. Then I flip the coin again, and I'm lucky because it tells me north or south. If it told me east or west, I would not move. And then I go there. And I just keep flipping coins. So these decisions are extremely simple because I'm flipping coins. And all of these decisions are one-dimensional. So even if you have million-dimensional space, not two-dimensional, these decisions will be very, very, very simple. Right? They'll be just one-dimensional minimizations. But it turns out this is not a heuristic. By doing the sequence of these one-dimensional random minimizations, you do better than the gradient descent, in theory and in practice. And as the dimension grows, the difference grows. Okay? So this is one of the key technologies enabling big data optimization. And you can throw the acceleration trick on top of this. It took the community a while to figure out how, but it can be thrown on top of it. And then it's even better, you can parallelize it, it's even better, and so on. So just keep doing it, and then boom, solved. Right? And in fact, this is how much better it is. You have gradient descent or something like this, and this RCD goes like this, and I skip this SGD, which is stochastic gradient descent, which is what almost everybody uses for training neural networks. The reason why they use that, and I have just 1 more minute, is because they are really interested only in solutions which achieve this accuracy of about 10 to the power minus 2 or 3, and then beyond that they don't care, because they'll be overfitting. So they're completely happy with running the algorithm just here, like one gradient step essentially, and then they stop. They just look at the data once or a few times, 5 times, and they stop. And the other tricks that I will talk about are parallelism, and I already thought that I wouldn't be able to do that, I'm not. And distributed optimization, duality, importance sampling. So importance sampling would, for instance, mean that you don't pick these probabilities uniformly at random, but with some biased coin. And then you can even improve, and you can see in theory how it improves. So I will stop at this point. Thank you very much. you.